Hi, it's me, Dr. Prasad Puthiyillam. My class number two on coordination chemistry. In class number one, I discussed about the introduction to coordination complexes. This is class number two. Here I'll be explaining about the transition metals. Okay, that 3D series, 4D series, all those things, and how to write the oxidation number, what are the possible oxidation states, and the electronic configuration of those possible oxidation states of transition metals. Okay, so magnetochemistry, class number two, introduction to transition metal atoms, electronic configuration. Okay, so transition metals, already studied that they are group B metals, or we also call them as group 2A, or between that of group 2A and group 3A in the modern period table. They are also called as base formers to acid formers, because the left side of the transition metal they are base formers, and towards the right side they become acid formers. They become produces acids. The compounds which are formed between that elements are becoming acidic nature. So the period 4 transition metals are called 3D series. The period 5 they are called as 4D series. Period 6 5D series, and period 7 6D series. This is because in period 4 the outermost orbital, the d orbital, or the filling of electron takes place in the inner shell, that is 3D, not in forest as such, but some rearrangement takes in certain cases. So it goes to the 3D series, that like just like a 1s2 2s2 2p6 3s2 3s2 3p6 3D, that 3D case. Therefore, we period 4 we call it as 3D series, and period 5 we call it as 4D series, period 6 5D, and period 7 they are 6D series. As well as we'll see what are the lanthanides and actinides, and mainly their name, their atomic number, their electronic configuration, the possible oxidation states, and its electronic configuration we'll take, because then we'll conclude with the D1 D2 to D10 systems. Although systems are important to analyze the magnetic properties of the coordination compounds, whether their pairing takes place, electronic pairing takes place when they are combined to form molecular orbital, or those it will support. Therefore, we'll see the basic of that, introduction of that. So I'll come out from this presentation screen. I'll go to another screen, that is the word file. Okay, so 3D series, I already given the table, because you already studied in lower classes which are the 3D series, scandium, titanium, and you have your own method to remember those elements, like Sachin Tendulkar, very crazy man, feels comfort near the comfort company of Zimbabwe. Like that, many methods that you can create your own creativity. You can try to remember the elements present in 3D series as well as 4D series, like that. Okay, so in 3D series, the first element, that is a scandium Sc21. Scandium Sc means scandium, that is I can write as Candium, scandium. The next one, that is titanium, Ti, titanium. The third one, that is vanadium, vanadium. Fourth one, that is chromium. Then comes manganese. Then comes iron. Then comes cobalt. Then comes nickel. Then comes copper. Then it is zinc. Okay, so these are the 3D series elements. Their atomic number starts from 21 to 30. While writing the electronic configuration, what we used to do, we'll write 1s2 2s2 2p6 3s2 3p6 and 3d1 4s2, or till that 3p6, that is the configuration of the noble gas argon. Therefore we'll take argon 18 as the base, and after writing argon 18, argon in square bracket 18, we will start continuing writing 3d1 4s2 3d2 4s2, like that, this electronic configuration. Okay, so here one thing I kept in a bold, that you can understand why it is so, because D has got a 5 sub levels, one each. If you take, that becomes 5, it will be more stable. Okay, so to get stability of the atom, or the ions, the arrangement of electrons takes place, that is explained, well explained, that also you studied in your lower classes. Okay, in case of chromium, this type of rearrangement is there. When it comes to 4D series, you can see so many such type of particular examples based on everything contribute towards the stability of that particular atom. Okay, so that is can be explained in some other classes. So here I'm not going to explain why it is so. So this is easy I explained. So the possible oxidation states of scandium, if you see, it cannot form plus one oxidation state, it cannot form plus two oxidation state. The stable oxidation state of scandium possible oxidation state is plus three oxidation state. Plus three oxidation state means from scandium configuration, three electrons are removed. That is two electrons from 4s and one electron from D. So it becomes 3D as 0. So I'll take from here. Okay, it becomes 3D 0. Okay, so the scandium plus 3 has got a 3D0 configuration. That is, it becomes the configuration of argon itself. Then titanium can have 3D2 system. Then it can have a 3D1 system as well as 3D0 system. All these three possibilities are giving stable configurations. Therefore, you can say titanium can exist in a plus 2 oxidation state, plus 3 oxidation state, and plus 4 oxidation state, and the electronic configuration also given. Vanadium can also form the same type, 3D2, 3D1, 3D0. So it can lose 2 electrons, then it becomes 3D3. When it loses 2 electrons, it becomes 3D3. That means plus 2 oxidation state. When it loses 3 electrons, it becomes 3D2, like that, plus 4, 3D1, plus 5, 3D0. All are possible electronic configuration or possible oxidation states of vanadium. In case of chromium, if we take, it can have 3D3 configuration, that is plus 3, and as well as 3D4, 4, 3D4, 3D3 are stable, that is plus 2 plus 3 is stable, whereas plus 4 is not stable. Then it becomes 3D1 as well as 3D0. They are also stable, they are also possible. Okay, so all these configurations are possible. This plus 2 plus 3 plus 5 and plus 6 oxidation states are possible for chromium. And this electronic configuration is also important towards our concept, that is coordination chemistry, magnetochemistry of coordination compounds. Then next one is manganese. Manganese can have a 3D5, 3D3, not copy paste. Okay, so 3D4 given there. It can have 3D5 also. 3D5, 3D4, 3D3, 3D2, 1 and 0. 3D2, 3D1 and 3D0. All these are possible for manganese. That is plus 2, plus 3, plus 4, plus 5, plus 6 and plus 7 oxidation states are possible for manganese. Even they are stable. In case of iron, you can have 3D6 configuration. 3D6 that is plus 2 oxidation state. It can have 3D5 also. It can have it possible oxidation state of 3D4 is also there, but 3D4 they are very less stable. Okay, therefore I'll highlight that one. 3D4 of iron, that is plus 4 oxidation state of iron, is very less stable. As soon as it formed, it will be converted into some other forms, but it is possible. It is possible to write plus 4 oxidation state for iron. 3D3 is also possible. Then 3D2 is also possible. 3D2 is also possible for iron. 3D7 is not possible. Okay, so 3D2 is also possible, but again it is less stable. Okay, so I'll highlight it. Therefore, I can say that in case of iron, plus 2, plus 3 and plus 5 oxidation states are more stable, whereas plus 4 and plus 6 oxidation states are also possible. Some cases it is possible, it will be formed. Then next case, that is cobalt. Cobalt can have plus 2 oxidation state, that is 3D7 actually. Plus 2 means 2 electrons from S will go. It will be removed, therefore it becomes 3D7. then it is 3d6, that is plus 3 oxidation state, then it becomes 3d5, that is plus 4 oxidation state. So 3d7, 3d6, 3d5, this plus 2 plus 3 and plus 4 oxidation states are possible for cobalt. In case of nickel, I can have 3d8 configuration. When we remove 2 electrons from the system, it becomes a 3d8. 3d8 is a stable configuration for nickel. Even 3d7 is also, that system also, it is plus 3 oxidation state is also stable in case of nickel. Okay, so with the nickel we have two stable configurations, two stable oxidation states, plus 2 and plus 3. With the copper, if you lose one electron, then it becomes 3d10, so it's stable. Okay, therefore with the copper, in case of transition metals of 3d series, the plus 1 stable plus 1 oxidation state is therefore copper. Okay, and it can also have 3d9 system, that is plus 2 oxidation state. So copper 2 plus and copper plus 1 are possible. Zinc can have zinc 2 plus oxidation state, that is a stable oxidation state for zinc. Okay, so these are the possible oxidation states and their electronic configuration. When you go to 4D series, 4D series, that is yttrium, zirconium, niobium, yes, Zimbabwe run with no ball, but man of technical caliber can run all those technical words, all those words that I use to remember the in the order of the elements. You can have your own method to remember Y, ZR, NB, MO, TC, RU, RH, PD, AG, as well as CD. Okay, the names are yttrium, YITRIUM, yttrium, and next one, that is zirconium, zirconium. Third one, that is niobium, then molybdenum, then next after molybdenum it is technetium, TICHNETIUM, technetium. Then comes ruthenium, ROTHENE, ruthenium, NIUM. Then comes rhodium, RHODIUM, rhodium. Then palladium, after palladium it is silver and cadmium. Okay, silver and cadmium. Okay, so these are the 4D series elements: yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, and cadmium. Okay, so their atomic number starts from 39, 39, 40, 41, like that up to 48. It's to write electronic configuration of these 4D elements. We'll take the noble gas configuration of that of Kr, krypton. Okay, its atomic number is 36. It becomes 41 5s2, 42 5s2, like that. The electronic configuration that you already studied in your lower classes. Okay, I'm bothered about their oxidation state, possible oxidation states, and that electronic configuration, and how we connect it to that D system, D1 to D10 system that is mentioned. I'll explain. Okay, so here with for D series, yttrium can have a plus 3 oxidation state, that is for D0, for D0. Then zirconium can have 42 is possible. 42 is possible. Okay, only highlight it came, but it is less stable. 42 is possible, but it is less stable. Then possible is 41. 41 is possible. 40 is also possible. Therefore, plus 2, plus 3, and plus 4 oxidation states are possible for zirconium. For niobium, we have 43 to 40 possibilities are there. So just take from here. Okay, I'll remove the highlight. Okay, then I'll take one more 43 I want. So So 43, 42, 41, 40, 0. That is plus 2, plus 3, plus 4, and plus 5 oxidation states are possible for niobium. Then we'll go to molybdenum. Molybdenum has got just like manganese. It has got a more number of oxidation possibilities. That is 44, 43, 2, 1, and 0. That is plus 2, plus 3, plus 4, plus 5, and plus 6. Okay. Then for technetium, we have plus 4 and plus 5 possibilities. Plus 4 means 2 from here. So 2 from here it becomes 44. So it is 4d4, 44 after 44, then 43, 42, and 41. 43, 42, and 41 are giving the stable oxidation state, that plus 4, plus 5, plus 6, and plus 7 oxidation states. In case of ruthenium also it gives a plus 4 oxidation state. Plus 4 oxidation state means how many number of electrons? 4 electrons we have to remove from the system. Then it becomes 4d4. Then it becomes 44. Okay, do I did mistake? So here it is plus 4 oxidation state. That means it becomes a 3. This becomes 2. This becomes 1. This becomes 0. Okay, so the possible oxidation state of technetium are plus 4, plus 5, plus 6, and plus 7. So case of ruthenium it becomes 44, 43, 41, and 40. Okay, all are possible. Okay, so plus 4, plus 5, plus 6, plus 7, and plus 8 oxidation states are possible for ruthenium. In case of rhodium, we have D6, D5, and D4, D3 systems are possible. I'll copy paste 1, 46, 46, then 45, 44, already it was 4, 43. 43. These are all the possible oxidation states for rhodium. Plus 3, plus 4, plus 5, and plus 6. Then for palladium, it is D8 system and D6 systems are possible. D8 system means that is 4D8, that is plus 2 oxidation state, 4D8, and D6 system, that is 4D6. Okay, so 48 and 40, that means a plus 2 oxidation state and plus 4 oxidation states are possible for palladium. In case of silver it becomes 4d10, d10, as well as what happened here, it becomes subscript, okay. So what is, it becomes a 4010, that is plus 1 oxidation state for silver, and also 49. Okay, now if you think about the stability of these oxidation states, okay, one more is there. I will finish it off. That is plus 2 oxidation state, that is 4010. Okay, so if you think about the possible stabilities, 49 with the silver, it is not that much stable. Therefore, but it is possible, but it is not that much stable. Then technetium also 43 is stable, 42 is not that much stable configuration. And in case of ruthenium D4, D3. D3 is not that much stable configuration. Even D1 is also not a stable configuration, stable oxidation state. In case of palladium also, D4, D3 is also not that much stable configuration or stable oxidation state. Therefore, we can say that yttrium has got a plus 3 oxidation state, zirconium plus 3 and plus 4, niobium plus 2, plus 3, plus 4, and plus 5, like that. Molybdenum plus 2, plus 3, plus 4, plus 5, plus 6, plus 7 is not there. Plus 7 is possible for manganese. Okay, we got it here. Okay, so in case of technetium also, ruthenium also. So you can take a screenshot of this and you can note it down also. Okay, now 5D series. 5D series starts with lanthanum, hafnium, like that. It is not lanthanides. Okay, I can see after lanthanum the atomic number 57 to 72. So that means there are a set of atoms present in between that of La and HF. We call them as lanthanides. Okay, so here it's HF 72 to 80, that is mercury till mercury. The electronic configuration we write after the electronic configuration of xenon, that is xenon F54. Electronic configuration already written here. The possible oxidation states also mentioned here. Okay, can take a screenshot of this. Can take a screenshot of this, and the less stable oxidation states also highlighted one. The highlighted one are the less stable oxidation states of their corresponding ions. Okay, so where I was, okay, so this one you have to take screenshot. Okay, so hafnium to lanthanum to mercury. Then 6D series elements, it starts with actinium, then jumps to rutherfordium to copernicum. Okay, so here also 89, 104 to 112. Okay, electronic configuration is taken as after Rn 86. Okay, the electronic configuration they feel they also have F orbitals, D orbitals, and this S orbitals contributing towards their properties. Okay, so the possible oxidation states and their electronic configurations also mentioned here. Now lanthanides. Lanthanides are the F block elements. Okay, till now we discussed they are D block elements. Now they are F block elements. Lanthanides starts with the cerium, prasidium, or those. Even electronic configuration also are given as such, because just we know the atomic number, we can write the electronic configuration by above principle, fill in the electrons, stability, everything we consider, and we'll write the electronic configuration. The possible oxidation states for lanthanides are lanthanides starts with cerium. Cerium we have plus 2 is possible, plus 3 is possible, plus 4 is also possible. In case of PR has got a plus 2, plus 3, plus 4, and plus 5 is also possible in case of PR. Then ND neodymium, it can have a plus 2 oxidation state, plus 3 oxidation state, and it can have plus 4 oxidation state also. So no. Then PM can have only plus 2 and plus 3 oxidation states. Okay, not equal 3, it is plus 3 oxidation state. Then samarium can have plus 2 and plus 3 oxidation state, same thing. Then euthyphodium can also have the same. Then comes gadolinium, can also have plus 2 and plus 3 oxidation state. In addition to that, it can have even plus 1 oxidation state also possible. Tellurium, it is the same oxidation state of that of gadolinium. Gadolinium. But I said gadolinium. Okay. Then dy has got a plus 2 plus 3 oxidation state, and the remaining all also have the same possible oxidation states. Okay, so plus 2 plus 3 is possible for remaining all lanthanides. Okay, these are the possible oxidation states. Okay, so these are the lanthanides and their possible oxidation states. Now actinides. Actinides starts with thorium. Thorium, that is plus 3 and plus 4 oxidation state. Then next one, it is plus 3, not there, here. Plus 3 and plus 4, as well as plus 5 oxidation state is also possible for that of a PA. Then it becomes plus 3, plus 4, plus 5, and plus 6. Paste. Plus 6 also possible. Okay. plus 3 plus 6 also possible. In case of next one more possible oxidation state is there. State becomes plus 7 is also possible. Then the same thing is possible for polonium. That is what, how much you got? 1 2 3 4 5. Okay. Then it is plus 2 plus 3 plus 4 plus 5 plus 6 plus 2 plus 3 plus 4 plus 5 and plus 6. Then for sammaranium, it is plus 3 and plus 4, plus 3 and plus 4 oxidation states. Even the remaining almost all has got the same electronic configuration, the same possible oxidation states. The last one is having only plus 3 oxidation state. Okay, so plus 3 plus 4 plus 3 plus 4 plus 5 plus 5 plus 6 plus 6 plus 6 plus 6 4 4 4 4 4 and 3. Okay, so some methods we have to use to remember all these possible oxidation states. Okay, now if you consider, so we draw the electronic configuration and possible oxidation states for most of the 3D series, 4D series, 5D series and 6D series elements. Then lanthanides and actinides, the possible oxidation states are also given, so that you can give the possible electronic configuration. Now we take the system for our consideration, that is like to understand the magnetic properties. It is easy to say that it is D1 system, D2 system, D3, D4, D5, D6, D7, D8 or D9. Or we can say, if I say Ti3 plus, Ti3 plus comes when immediately when we should remember that it is D1 system, that is its outermost orbit has got one electron. Therefore, while connecting the molecular orbital, one electron, whether electron pairing takes place, like that, all those things, it will easy for us to understand. Therefore, this one also we can take a screenshot so that it will be easy. So whenever comes whenever calculation, if we calculate the given coordination complex, the oxidation state of Fe is 6 plus. 6 plus is D2 system. Usually we won't discuss D1, D2, D3 as such. D4, D5, D6 and D7 systems are having more uh, related to the magnetic properties, in which D5, D6 and D7 are very important towards the magnetic property explanation, towards the quadruple pole shifting and all, to explain that it is very important to understand what is D5, D6 and D7 systems. Okay, so this about okay, even D10 is also there. So this about the second class of coordination chemistry. Just we are revising what we already know. Okay, we know the 3D series, you know 4D series. Just to practice session, like that you can take it out. Write the element name or configuration and try to write down the possible oxidation state. It's a practice. Okay, so then you can note down which are the systems. Mainly should know which are the D5 system, D6 system and D7 system, to understand, to easily understand what are the magnetic properties of coordination complexes. So I'll come out from the screen share. So that's all for class number 2. Thank you very much for watching.